In this video, we shall discuss when do we need atomically flat substrates in scanning probe microscopy experiments. So if you want to know more about different substrates and their qualities, you can look at the respective video. I made a separate video on that. When preparing samples for atomic probe microscopy, which is a branch of scanning probe microscopy, uh, scanning probe microscopy is a larger term, especially particulate samples. If you have larger particles, a substrate must be chosen on which to mount the samples. You need to have a substrate, but now the question arises: do you really need atomically flat substrates? And how do you know that it is atomically flat? How will you test it? In the case of very large samples, rough samples, or concentrated preparations like agglomerates, the nature of substrate can be unimportant. Please note that. But for many cases, it is crucial for correct sample preparation and good results. If you have very large samples and a lot of aggregates, for example, large cells where you're not interested in like DNA level work, then you don't need to worry about the surface roughness. You can take cover slips, glass slides, and all kinds of things. But if you want to do high resolution work and you're looking at individual molecules, then you need to have atomically flat substrate, because any additional error from substrate roughness will add on to your features, and your features will become unreliable. For imaging of larger features, a substrate with higher roughness can be adequate, as well as the roughness. The chemical nature of the substrate can also be important. Sometimes when you do the modifications of a substrate, then you may end up manipulating the pre-coated roughness of the substrate. For example, if you are not careful and you're depositing gold, chromium, or something else onto an atomically flat substrate, so there is no guarantee that after coating you're not deteriorating the flatness of the substrate. Similarly, if you are trying to coat silane, for example, APTES or APTMS, mercaptocillin, or amines, silanes containing amine functional group. So many times, if you have high humidity, so it can polymerize and make a thick coating of silane onto the silicon or glass substrates. So you have to be extra careful there. Again, it depends upon what kind of experiments you are planning. And I would like to add one more point here, that it also depends upon the tip you are using. If you are using super sharp tips, then obviously you have to have that. For that kind of experiment, you have to have compatible atomically flat substrate. And if your tip radius, its radius of curvature itself is very high, and the tip is not of that quality, it's old, worn out, then no matter how flat substrate you take, your images will always be convoluted by the bad quality tips, blunt tips, or sometimes you have to put an additional layer onto the cantilever, the AFM cantilevers, the tips. Sometimes you want to magnetize the tips, right? And sometimes you want to make it functional, so you have to coat it first with gold and then your desired functional molecules. Sometimes you want to just directly coat some molecules, some ligands over the AFM tips. So all these things can add up to the radius of curvature of your tip. And then the convolution effect get compounded right here. And I mentioned in a separate video that highly oriented pyrolytic graphite, mica, they are both can be easily cleaved in their atomically flat substrates. And but chemical modification of HOPG is not easy. You don't have free dangling bonds, and you don't have sort of activity at the surface. You can make the graphite surface active by some chemical treatments. It's possible. On the other hand, gold is highly stable material, but it is extremely simple to modify chemically. But as I mentioned, that it's not easy to produce extremely flat surfaces when you deposit gold. It's considerably more difficult than for mica and gold. That's it for this video. I hope it was useful. Send your comments at my email.